Imagine you're driving in a completely unfamiliar city at night.
Oh, the worst.
Right. It's stressful. You're trying to find a specific address, maybe a restaurant for a dinner you were already running late for. So you look down at your phone's map app and you see that little blue dot, pulsing away, tracking your progress down the street.
And you just trust it.
Exactly. You trust that dot implicitly. It's like a reflex at this point to assume the digital representation of your location perfectly matches physical reality.
Yeah, I mean, we treat satellite navigation like it's a foundational law of physics. It just operates silently in the background, underpinning almost every logistical thing in our modern lives. So we simply assume it's, well, absolute truth.
Right, but the maritime intelligence reports and the engineering breakdowns we're diving into today, they reveal a pretty terrifying reality. That dot is wildly easy to fake.
It really is.
So for today's deep dive, we are looking at how the world's massive cargo ships are being systematically gaslit by manipulated GPS signals. We're going to explore the hidden fragility of the navigation systems moving millions of tons of global trade. And we'll unpack the brilliant, old-school aerospace technology stepping in to save them.
And the documentation on this is just staggering because that highlights a fundamental flaw in the architecture of global shipping. We're looking at a vulnerability that extends way beyond, like a simple hardware glitch.
Yeah, the stakes here dwarf a missed highway exit.
Yeah.
The modern merchant vessels that act as the circulatory system for global commerce, they rely on GNSS, global navigation satellite systems, like GPS. They rely on it in the exact same way you rely on your smartphone.
Which is to say, entirely.
Entirely. And the vulnerability becomes really apparent when we look at the bridge of a massive container ship. We have to ask, what happens when every single system in the room agrees on a perfect, synchronized lie?
Oh, engineers actually refer to that nightmare scenario as a common mode failure.
Common mode failure, right.
Yeah. When you walk onto the bridge of a contemporary commercial vessel, you're surrounded by this crazy array of highly sophisticated interfaces. You've got the ECDIS.
That's the electronic chart display and information system, right? The digital maps.
Exactly. And then you see the AIS, which is the automatic identification system that's broadcasting the vessel's location, speed, and heading to all the other ships in the area. Add in radar overlays, voyage data recorders, master clocks.
It creates this impression of a highly redundant, fail-safe network. I mean, it looks like an airplane cockpit. You assume that if one screen malfunctions, the others are just going to compensate.
But that redundancy is a total illusion.
That blew my mind.
Right. On a typical merchant vessel, every single one of those critical systems draws its positional data and its timing synchronization from one single GNSS antenna.
They're all drinking from the exact same digital well.
Precisely. If that lone satellite feed is compromised, the corruption just cascades across the entire navigational stack simultaneously. So the electronic chart shows the ship safely in the center of the deepwater channel. The radar overlay aligns perfectly with that chart.
And the AIS confidently broadcasts to the whole world that everything is totally fine.
Yeah, the environment maintains perfect internal consistency. Even though it's entirely detached from physical reality, the crew has no immediate reason to suspect a malfunction, because the computers possess absolutely zero alarms for misplaced confidence.
And we aren't talking about a scenario where the antenna just breaks or the signal drops out.
No, not at all. If the receiver loses connection, the system throws a massive, blatant lost GPS error. You know it's broken.
Right. But the threat detailed in these intelligence reports is far more insidious. It involves active signal manipulation, specifically a technique known as meaconing or carry-off spoofing.
Yeah, because jamming a signal is just a blunt force attack.
Yeah.
You're just blasting radio noise on the GPS frequency until the ship's receiver goes completely deaf. Spoofing and meaconing in particular is an elegant deception.
It's like hacking their reality.
It really is. A malicious actor captures a valid satellite signal and rebroadcasts it to the target vessel. But they introduce a highly controlled artificial time delay into the transmission.
So they feed the ship's computer its own language, just subtly altered. And because the fundamental structure of the signal remains valid, the ship's processors just accept the data as authentic.
Which leads to this terrifying phenomenon. It's frequently observed in contested waterways like the Strait of Hormuz. The reports refer to it as the slow walk.
The slow walk. The attackers gradually alter the timing, causing the ship's calculated position to slowly drift away from its actual physical location.
And the gradual nature of the drift is what makes it so lethal. A ship's autopilot is programmed to diligently maintain the plotted course over the seabed.
So if the spoofed signal tricks the computer into believing the vessel is drifting, say, 50 meters to starboard.
The autopilot automatically commands the rudder to steer port to compensate.
Right. And the cross-track error alarms the safeguards that are supposed to scream if the ship wanders out of its lane. They never trigger because the software believes it is just correcting a minor environmental drift. It thinks it's doing its job.
Exactly.
Meanwhile, out in the physical world, the ship is literally moving sideways.
Yes, it is crabbing out of the safe shipping lane.
And I actually need to bring something up here. In a previous video instruction we looked at, someone suggested that to catch this, you could just use a vernier caliper on the digital charts to check the distances.
Oh, wow. No.
Right. It's so wrong. I mean, please do not use a vernier caliper on the charts. That is completely absurd and not how maritime navigation works at all.
Yeah, definitely don't do that. You'd use parallel indexing on the radar, which we'll actually get to later. A caliper on a screen isn't going to save you from a spoofed GPS.
Exactly, because physically the ship is sliding sideways into danger. The crew feels completely secure, looking at green lights across all their instruments right up until the hull tears into a submerged reef.
That's terrifying.
The sources included intelligence photos of a massive Japanese cargo vessel fully beached on a rocky shoreline. It was miles from where its navigation systems claimed it was. It makes the severity of this threat incredibly visceral.
And the fallout extends way beyond the immediate physical grounding, because GNSS also dictates the master timing for the vessel's digital infrastructure.
Oh, right, the timestamps.
Yeah. During a meaconing event, the ship's voyage data recorder, which is the maritime equivalent of an aviation black box, it's logging fake coordinates synchronized to fake timestamps.
So in the aftermath of a catastrophic collision, the digital evidence is just completely corrupted.
Marine investigators can't even reconstruct the sequence of events because the timeline itself was spoofed.
You know, hearing how easily a $100 million modern vessel can be covertly hijacked by a few altered radio waves, it actually makes me nostalgic for the era of wooden ships.
I could see that.
At least in the 17th century, a pirate couldn't hack a magnetic compass from 50 miles away, you know?
That's true. And ironically, the evolution of maritime navigation actually points us directly toward the mechanical marvel that was designed to neutralize this modern cyber vulnerability.
Ah, dead reckoning.
Exactly. Long before satellites or lasers or radio beacons, global exploration relied entirely on dead reckoning.
So let's use the classic analogy from the sources of a Dutch sailor in the 1600s leaving Amsterdam to cross the Atlantic. The navigator knows their exact starting point at the harbor dock. They check their magnetic compass, point the bow west, and set sail.
But a compass only dictates heading. It cannot plot a specific location on a blank map.
Right, for that you need to calculate distance.
Plotting a new position requires calculating the physical distance traveled. And that requires knowing your velocity and the time elapsed. You multiply the speed by the time, and you derive the distance.
Then you draw a line representing that distance from Amsterdam heading west, and that endpoint becomes the ship's new estimated position.
That mathematical process is dead reckoning.
And the ingenuity is in how early mariners measured that velocity. They literally tossed a piece of rope over the stern of the ship.
Yeah, a log line.
Right. The rope had physical knots tied into it at very specific intervals, and it was attached to a piece of wood designed to catch the water. As the ship sailed forward, the rope unspooled, and a sailor would use an hourglass to count out how many knots slipped through their fingers over a specific duration.
And that physical measurement is the literal origin of the term knots.
Which is crazy to think about.
It is. It remains the standard unit of speed in global maritime and aviation industries today. A modern 747 pilot still communicates their airspeed using the terminology of a Dutch sailor dragging a rope through the Atlantic.
So at its core, dead reckoning is simply taking a known starting point, physically measuring your movement and updating your reality based on that.
Exactly. Now fast forward to the height of the Cold War in the 1960s. The military was developing the F-104 Starfighter.
Famously dubbed the missile with a man in it.
Yes. The Department of Defense needed a navigation system that could not be jammed by Soviet electronic warfare, could not be spoofed, and did not rely on ground-based radio antennas.
So aerospace engineers essentially digitized that Dutch sailor. They created the Inertial Navigation System, or INS.
And the defining characteristic of an INS is its absolute, uncompromising independence. It's frequently described by engineers as a stubborn teenager who refuses any assistance from the outside world.
I love that analogy. It's a sealed metallic box. It doesn't look for satellites in orbit, and it doesn't listen to terrestrial radio frequencies. It calculates position entirely based on the internal physical forces it experiences.
Making it fundamentally immune to meaconing, jamming, or network outages.
But applying the principles of dead reckoning to a supersonic jet presents a staggering leap in complexity. I mean, dragging a rope works perfectly for a wooden galleon moving relatively slowly along a flat ocean surface. But a starfighter jet operates in 3 dimensions at Mach 2.
Yeah, it pitches, rolls, and yaws violently.
So wait, there's a massive physics hurdle here. How does a sealed box with no windows, receiving zero external signals, actually feel its complex trajectory through 3D space?
The mechanism relies entirely on inertia. Consider the physical sensation of being blindfolded in the passenger seat of a car. You have zero external visual references. You can't see the road signs or the horizon.
Yet I can still build an intuitive map of the journey. Like if the driver floors the accelerator, my body is shoved back into the upholstery.
Right.
If they slam on the brakes, I strain against the seatbelt. A sharp left turn throws my mass hard to the right. My brain translates those physical forces, the inertia, into an understanding of movement.
And an INS utilizes highly sensitive instruments called 3-axis accelerometers to perform that exact translation mathematically. These sensors measure the minute changes in velocity across all 3 spatial dimensions.
Longitudinal forward and backward, lateral left and right, and vertical up and down.
Exactly. The internal computer takes that acceleration data, factors in the elapsed time, and calculates the exact distance covered.
The math is straightforward, but I can anticipate the fatal flaw in the physics here.
Oh, yeah.
Yeah, let's return to the blindfolded car passenger. I am sitting in the car, and I suddenly feel myself being pushed firmly back against my seat. That sensation could mean the driver just accelerated rapidly down a flat highway. Or it could mean the driver just parked on a 20-degree uphill incline. Gravity is pulling my mass backward. Without seeing the horizon out the window, I have no way to distinguish between forward kinetic acceleration and the backward pull of gravity on a tilt.
Bingo. You've isolated the fundamental limitation of an accelerometer. It cannot differentiate between kinetic acceleration and gravitational force. If a fighter jet pitches its nose up into a climb, the Earth's gravity pulls backward on the longitudinal accelerometer. If the navigation computer interprets that gravitational pull as negative forward acceleration, it ruins the math.
The entire navigational solution just collapses instantly.
Completely. So the engineering challenge is finding a way to completely isolate those sensitive accelerometers from gravity's interference, regardless of what the aircraft is doing.
And engineers solve this by mounting the accelerometers on a central platform suspended inside a series of concentric rotating rings known as gimbals.
Right, and attached to these gimbals are gyroscopes. Gyroscopes are essentially rapidly spinning wheels that, due to the conservation of angular momentum, rigidly resist any change to their orientation in space.
So as the fighter jet executes a barrel roll or dives toward the Earth, those gyroscopes fight the movement. They physically force the gimbals to counter-rotate,
Keeping that inner platform perfectly flat, artificially parallel to the horizon at all times.
The jet can fly completely inverted, and the small platform inside the box remains perfectly level. And because the platform never tilts, gravity only ever pulls straight down through the vertical axis. It never bleeds into the horizontal or lateral accelerometers.
The mechanical precision of those gimbals is an absolute masterpiece of mid-century engineering. However,
There's always a however.
there is. Maintaining a platform perfectly level relative to a fixed point in space introduces a paradox when navigating a planet. The Earth is a sphere, and it is rotating.
Right. So if a gyroscope holds its orientation perfectly rigid, and an aircraft flies from the equator toward the North Pole, the curvature of the Earth drops away beneath it.
Exactly. To the pilot, it appears the gyroscope is slowly drifting. But in reality, the platform is maintaining its orientation while the planet curves.
So the platform is no longer parallel to the ground below. Gravity bleeds into the forward sensors again, and the math fails.
To counteract planetary curvature, engineers implemented an active feedback mechanism based on the work of physicist Maximilian Schuler.
The sources refer to this as the Schuler loop, or the magic loop.
Yes, the accelerometers on the stabilized platform measure the aircraft's current speed. The computer processes that velocity, calculates exactly how fast the aircraft is traversing the curve of the Earth, and sends an electrical current back to the gyroscopes.
So the system intentionally applies torque to the gyros. It physically forces them to tilt just a tiny fraction of a degree.
It commands the gyroscopes to rotate at the exact rate the Earth is curving beneath the vehicle.
It's like the system continually pulls itself up by its own bootstraps. It uses the level platform to gather accurate speed data, then uses that speed data to continually adjust the platform to keep it level.
It creates a continuous closed-loop conversation between the mathematical calculations and the physical mechanics. It forces the platform to oscillate like a theoretical pendulum whose string extends to the very center of the Earth.
Naturally seeking the true vertical horizon. It takes a localized law of physics and actively bends it to accommodate a planetary scale. It's brilliant.
It really is.
But let's examine the reality of operating a completely closed-off system over long durations. Because, a microscopic fraction of a millimeter of friction in a gimbal bearing, or a tiny rounding error in the processor's calculus over a 12-hour flight or a 3-week ocean voyage, those minuscule errors will inevitably compound, right?
Yes, the system will drift. Inertial drift is the acknowledged Achilles heel of the technology. An INS does not provide permanent positional accuracy.
Right.
If a commercial airliner flies across the Pacific relying solely on its internal physics, its calculated position will be miles off course by the time it reaches the opposite coast. The core value of an INS is not permanent accuracy. Its value is continuity and absolute incorruptibility.
And this highlights a fascinating divergence in how different industries approach modern navigation. If we analyze commercial aviation or naval warships, their architectural design treats the INS as the primary source of truth.
Yes, the flight management computer intrinsically trusts the internal physics because it knows those physics cannot be hacked by an external adversary.
Knowing the system suffers from drift, the aircraft uses external GNSS, the satellite GPS, to periodically check and correct that internal drift.
The aviation paradigm utilizes the external signal to validate the internal physics. The maritime industry, specifically the commercial merchant fleet, operates completely inverted to this logic.
Which is the scary part. Modern cargo ships are designed to use the external satellite signal as the absolute truth. They blindly trust the data transmitted from orbit.
And this brings us full circle to the slow-walk gaslighting vulnerability we discussed earlier, with the ship moving sideways.
Exactly. When a meaconing attack tells a cargo ship it is drifting to starboard, the ship simply steers port to compensate. It lacks an internal physics-based system to step in and say, wait, my accelerometers did not feel any physical current pushing us to the right.
Securing global shipping requires merging these two philosophies through a computational process called sensor fusion.
Sensor fusion.
Yeah. In modern architectural diagrams for advanced navigation or autonomous vehicles, you will notice multiple data streams converging into a mathematical block labeled the Kalman filter.
The Kalman filter. And this is way more complex than just a simple switch flipping between GPS and INS, right?
Oh, absolutely. It's a recursive algorithm that acts as a rigorous mathematical referee. It takes the incredibly precise but highly gullible data from the satellites and pairs it with the drifting but absolutely incorruptible data from the internal accelerometers.
The reports explain it by assigning mathematical weights.
Yes. The Kalman filter continuously calculates the statistical variance, or the probability of error, for both sensors in real time. It operates using complex matrices to determine covariance.
So it doesn't simply ask, where are we?
No, it asks how confident is the satellite receiver in its position and how confident is the inertial sensor in its acceleration. It assigns mathematical weight to each input based on its historical reliability.
Let me personify this, because I love this analogy. It is like having two vastly different co-pilots in the cockpit.
Okay, let's hear it.
So the GNSS is a brilliant mathematician. He provides pinpoint coordinates down to the centimeter, but he is incredibly naive and will believe anything a malicious hacker whispers in his ear.
Fair enough.
The INS is a stubborn, slightly forgetful old sailor. He might misjudge the exact distance traveled over a few days, but he never, ever lies about what he physically feels.
Right.
So the Kalman filter sits between them, forcing them to relentlessly cross-examine each other's work.
That's a perfect way to look at it. Applying that referee logic to a spoofing attack demonstrates its brilliance. Let's say a bad actor captures the satellite feed and subtly alters the timing, attempting to trick the ship's computer into believing it is suddenly accelerating forward at 15 knots.
Okay, so the gullible mathematician accepts the altered signal and begins plotting the fake accelerated course.
But the Kalman filter immediately cross-references that claim with the old sailor. The algorithm asks the internal accelerometers, did we just accelerate to 15 knots?
And the INS checks its physical inertia and replies, I felt zero physical acceleration. Our state has not changed.
Exactly. Because the external data completely contradicts the internal physical reality, the Kalman filter's probability algorithms immediately flag the GNSS data as mathematically invalid.
It triggers a position integrity alarm, actively isolating the compromised satellite feed before the autopilot ever commands the rudder to turn.
The vessel is entirely insulated from the deception.
The elegance of that solution is deeply satisfying. Sensor fusion completely neutralizes the threat of the slow walk, but honestly, that raises an incredibly frustrating question.
I think I know you're going to ask.
If the technology to physically immunize global shipping against these cyber attacks has existed since the Cold War, why isn't every massive container ship currently running a Kalman filter and an advanced INS?
The barriers to adoption are almost entirely economic. Implementing a high-grade inertial navigation system, specifically the modern iterations, utilizing fiber optic gyroscopes that shoot lasers through miles of coiled glass to measure rotations area, it's an immense capital expenditure.
And commercial shipping operators function on razor-thin margins. Every upgrade must demonstrate a clear return on investment.
Exactly. Installing a fiber optic gyro does not make the cargo ship travel faster. It doesn't reduce the fuel burn, and it certainly doesn't add space for more shipping containers.
It serves only to mitigate an invisible risk. Convincing a corporate boardroom to spend hundreds of thousands of dollars per hull to solve a cyber problem they haven't personally experienced yet, that's a monumental challenge without external pressure forcing their hand.
It really is.
So how are ships surviving hot spots like the Strait of Hormuz right now? The maritime intelligence reports indicate spoofing happens there daily. If they lack INS, why aren't ships running aground every hour?
Well, maritime strategists refer to this as the Hormuz paradox. Critics of INS adoption argue that since ships navigate these jammed environments frequently without crashing, the expensive upgrades aren't necessary.
But that ignores the reality on the ground or on the water, right?
Completely. It ignores the fact that navigating successfully in these zones relies heavily on unsustainable human intervention. The industry is currently shifting an immense unfair burden onto the bridge crew.
Yeah, when the satellite feed is compromised, the officer of the watch must immediately transition to extremely high workload manual fallbacks. They revert to techniques like parallel indexing.
Which is what we mentioned earlier.
Right. And just to reiterate, this is where the navigator manually draws electronic lines on the radar screen, matching the sweep of the radar against known coastal features to verify their distance from the shoreline. Ensuring the digital map isn't lying, not using a vernier caliper.
Exactly. They are manually piloting a 300-meter-long floating skyscraper through one of the most congested waterways on Earth, all while actively mitigating a cyber attack.
The intelligence reports aggressively call this out as operational survival, not systemic integrity. It fundamentally relies on the crew realizing they're being spoofed.
Right. If the slow walk is subtle enough, the human operators won't know to start parallel indexing until they hear the hull grinding against the ocean floor.
So if the slow-moving international maritime regulators aren't mandating this technology tomorrow, what is the actual catalyst that will force the industry to upgrade?
The paradigm shift will be driven by the insurance sector, specifically underwriters and P&I clubs,
P&I clubs.
protection and indemnity associations. They are mutual insurance pools where ship owners band together to underwrite massive maritime risks and environmental disasters.
Oh, I see.
If a fully laden oil tanker runs aground in the Red Sea because it followed a spoofed GPS signal into a reef, the financial fallout hits the wallets of every ship owner in the club.
So the underwriters are going to investigate the bridge systems and ask a very pointed question. Why didn't this $100 million vessel have a way to independently verify its own position?
Exactly. When an underwriter determines that a ship lacking independent inertial verification is fundamentally unseaworthy for high-risk corridors, a calculus changes overnight. You'll see astronomical premium hikes or outright trading restrictions for vessels without sensor fusion.
Because the financial markets and mutual insurance pools evolve far faster than international regulatory bodies.
Always.
Yeah.
There's also the inevitable push toward mass maritime autonomous surface ships. The maritime industry is pouring billions into developing self-driving cargo vessels.
And an autonomous ship is a non-starter without internal inertial verification. A computer algorithm cannot look out the bridge windows, observe an island dead ahead, and intuitively realize the electronic chart is malfunctioning.
Sensor fusion is the absolute foundational prerequisite for any autonomous navigational architecture.
Synthesizing this entire landscape, we are witnessing a profound philosophical shift in how the world navigates. For the last 30 years, the singular goal of navigation was positional accuracy. GPS gave us incredibly precise coordinates.
But the priority has evolved. The goal is no longer just positional accuracy, it is positional credibility.
Positional credibility, I like that. We are transitioning from a navigational architecture designed to blindly accept data to an architecture built on rigorously questioning and verifying data against the physical laws of the universe.
It's a striking reminder that as our world becomes increasingly digital, we still rely heavily on robust, old-school physical principles to keep us grounded in reality.
Yeah, from the terrifying vulnerability of common mode failures to the 1960s genius of gimbals and the Schuler loop, we've seen why the gullible mathematician of modern GPS desperately needs the stubborn old sailor of internal physics.
The integration of the two creates an incorruptible referee, ensuring the digital map matches the physical world.
And that leaves me with a somewhat unsettling thought for you, the listener, to mull over. We started by picturing that map app on your phone and the blue dot you trust without a second thought. As our everyday routines become relentlessly automated, from the autonomous taxis we ride in to the delivery drones dropping packages on our driveways, all relying on the same external, highly spoofable signals, how long will it be until the personal devices in our own pockets require their very own internal inertial referees just to prove to us that the digital reality they are presenting is actually real?
A genuinely fascinating question to close on.
Thanks for joining us on this deep dive. We'll catch you on the next one.